the technology.
Sure,
Okay,
sure.
please. Yeah, thank you.
Sure.
Please go ahead.
Ek, we are live. Okay, fine.
Yeah.
Yeah. Um, Greetings, everyone. Welcome to the third session of ML Math Club here with us at Technojam. And today we have a very distinguished personality with us. And so I believe everyone is joining now. Great. So, yeah, today we have with us Dr. Jayakumar Singaram. Sir is the founder of Epigon Media Technologies Private Limited, an ARM ambassador, as well as a signal processing engineer at Mistral Solutions. Sir is a PhD from IIT Bombay, and as we all know, he is a great personality, and his work is formidable in the fields of aeronautical engineering, as well as machine learning and deep learning. So today we have Sir with us who will be guiding us and will be taking a session for data in motion, transitioning from data to networks. Yep. So over to you, sir.
Thank you, Anurag. Thank you, TechnoJam. It is an interesting name, the club name. I'm so happy to hear such a good names for the club. And also thanks to Calcutta University for giving me this opportunity to interact with young generation students and that to, upcoming data science related students. And also Tech, the design club. I think they're also, part of this group. I love to thank them also. So, and in particular, I'm more interested in sharing kind of a what you call knowledge base which we acquired in the past may not be very far, long duration. This uh, presently up to 2012 only most of things happening. So it's only 12-year history. What we having it, but before that there was a bit of work that is never been considered as a work. It is voice is okay, or you want to increase little more?
No, sir, it's fine. It's
Okay,
looking good.
so the before 2012, there was a work under the name of computer visions. Things, after 2012, there are only two things which we have before 2012 or after 2012. So I had opportunity to, work certain things after 2012, formally in the place called Watson, IBM Watson's. So that's a place I draw a lot of inspirations. It's one of the popular machines. Of course, even now it is available. So when you have a time, please do look at it in our club. It was a IBM's catalog service called IBM Watson's. So that's a thing when we kind of a base for me to launch my learnings apart from, and have hands-on experiments and small applications and certain things to get along with that. I do recommend please do look at those things as well. I do have references down. So with this on a short introductions about the 2012 note, I'm keep telling about 2012 because that's defining the kind of birth of AI formally into the present generations in particular semiconductor industry and then related to application industries. So, here I've been, given a nice introduction. Thanks, but I'm so happy to have this ARM ambassador one. It's a very recent one. November, I think November 10th or 15th came up. It was a very happy news for all of us to share. I think, we can do a lot more into that with this, portfolio in our hand. And ARM is, I'm sure most of you know, not most, all of you might know that ARM is the topmost processor IP company in the world, which is single-handedly occupied almost all the mobile phones, so whether Android phone or iPhone, like of course no other phones are there now. So the phones essentially like a Windows phone, not much Google Pixel. Everywhere this ARM processor is running in the background as a computing engine for communications, GUI, OS, and everything. So Android runs on it, iOS runs on it, like so that company is one of the formidable company in the semiconductor industry. They had a philosophically, they never made a devices. Of course, they would have made something, but they had a philosophically very different concept than unlike other companies like Intel or AMD. Intel and AMD, they do sell the silicons, but we cannot make those silicons, and they will sell the boards and silicons and things like that. But they sold that IPs called intellectual properties and ready to manufacturing on IPs, which is licensed to the smaller company, might be even a startup company or even a big company like Apple also. That the companies will take those IPs and then make their own silicon, right? Then that silicon will become part of the devices. So it's a customizable silicons from, but IP comes from ARM. ARM essentially, if you look at it, they're there everywhere in the mobile phone. They have a very big vision for the embedded world, like essentially like IoT segment where the nano smaller devices, very smaller devices, which they're all like in and around the home, in and around the vehicles, in and around drones, in and around airplanes, all the places, a lot more devices going to come in and around. Like olden days, we had a watches, and you may not be seen when we had a time we had a watches and specs and so. But all the specs have become AR/VR specs, and watches become like wearable things. So a lot more things are happening around. We can have sometimes to look at this related things, how we can make use of it. Okay, so today this mathematics is essentially one of the key things for us to move ahead in the knowledge world, where that things are dominated by computing and associated things. When we do computing, we need instructions, we need a machines, we had to teach the machines, or we had to make the machine to run. For that we need a lot more infrastructure to do that. Formally, that's the place which we essentially the semiconductor industry going on. I'll take you through what kind of mathematical things which is evolved around this AI world. Of course, there is no, new things happening as such in the mass, but they were there. But say industry taken certain beautiful things and started using it. So because of that, that kind of mathematical things become very popular, and it's scaling up very well in the academic world also. Of course, apart from the mathematics, kind of models, we need a kind of a data. That's what we call data set zone. We'll cover both, but more we spend time on the model zone if there is objection from all of you. So in the model zone, of course, these are all there. This link is there when even not now, tomorrow also you can look at it, correct? Anurag will share with this link, of course. It is there in a part of our, things. You can share it all, this can be shared as well easily. So, you can, it is there in a, shall I share the link or you guys confound it?
Sure, sir. I have shared the link, and right now we will be dropping that on the chat, live chat as well.
Super. It's so nice of you, madam, because the link always helpful. Sometime, what happened is the visibility may not be good when we do this one. With the link there, they can go directly onto that and then get 100% realistic view on that. That way, web is helping us for us to remotely. So the model zone, I know there is something like flickering here. So it's called mathematical theory of learning systems. All of we know like children learns, we all learn. Teachers made us to learn something, our parents made us learn something. But what does it mean learning system? System means non-living things like a bus, car, lorry, aeroplanes, or trains, or like there are like systems like transport systems, like healthcare systems. But how do what does that means learning systems? Are they going to do learning? That's a kind of very, very interesting. I think you are all lucky to be in, be a student in this point time frame. So that will, take you a long way in your, life and professional life, because they're all happening now. The system started learning. Now the question comes is if the system learning, who's going to teach the systems? How to make the system learn? To make the system learn, what are things we have to do for the system to learn? These are all associated questions come up. Those questions become industrial revolutions now. Those questions are, fueling the industrial revolutions for the, presently last 1.5 years. And that has become a very, very powerful across the globe. People lose the job, people get a job, the companies make a silicons, companies make a storage, companies sell the too many silicons. There are companies who are not in the AI, they close, trying to close the companies. There, certain things are happening around. So there are good things, there's a bad thing, there are a lot of things happening a lot in 18 months because of the one thing called learning systems. The learning systems, when the fundamentally something learns means, it doesn't know before that. If I say I learned this one, I learned from techno jam people that today raining in Delhi. Suppose I learned, but 2 hours before I did not know that information, so I did not learn that. But when I say I learned this, that means that informations or that knowledge base is not with me before I learned that. So system also same thing. 1 hour before the system may not be learned of the conditions of the weather condition in Delhi, but now the systems, if the learning system is around, it learn that weather conditions in the Delhi. So then people can understand what will happen after 20 minutes. Is it okay for me to take a evening walk? Then the system will tell, predict, and then tell, it's okay or not okay, it's good. So certain things happen. So the learning systems, why do we do? I'll formally take through that. So that it has for a formal way of doing that. First thing is theory of learning systems. What is that theory which we are going to do? Then data to networks. How that data all become like a networks. Then what is that model? Then what is the restricted Boltzmann machines (RBM)? These are the four things which you do. In the bottom, you have a references. Please, when you have a time, you can click and then see the references as well. Okay, these are all one place, so you don't need to go to this side or that side. This is a place which we did. With your permission, so now let me get into the theory of learning system, which formally. A theory of learning systems, what is happening is when we learn certain things called uncertainty. Uncertainty means if you do not know what going to happen after 2 hours, then I'm very uncomfortable, correct? People will be uncomfortable because they do not know what going to happen after 1 hour or 2 hours in their standing railway station. If they do not know whether train going to come or not, or whether train 8:30 train going to come 8:30 or 9:30 or tomorrow morning, in that uncertainty drives something called uncomfortable for the passengers, correct? That's for a human being. But how does that is going to play major role in the machine learnings, like theory of learning systems? If there is no uncertainty, then there is no unlearn, there is no learning. Actually, everything is known. That's the other part of the story actually. So we drive that one very carefully. Suppose if you see here, like a temperature is a kind of variable. If you see the high temperatures, the particles are moving, like balls are moving far away, and the full of that. We keep reducing the temperature down, 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 down. Now it's become almost like very down. So their movement is restricted on the vertical, and these are all coming down. After some time, they reduce the temperature still down. They become a standstill. So the ideas are the network also the similar situation. There is no difference. This is what essentially our Nobel Prize winner Professor Hinton understood 1986, and then he converted this idea of like Boltzmann machines. Essentially, Boltzmann had founded this theory of gas particle at various temperatures where they'll occupy the what velocity they'll have, how much distance they jump, every hidden collision, whether this jump is computable. Or, how do we measure them? These are the questions, fundamental question asked by physicists, popular physicists that point at Boltzmann's. Of course, I'm supported by that Maxwell as well, but not many people supported him that point at time. So the theory of gases, like essentially the branch out from thermodynamics, which you would have studied in the first years, correct? So the thermodynamics second law, which they introduce a new thing called entropy disorders. And that's a place the whole thing was went on, but there is a people agreed, people disagreed. That point at time, there is a, I mean, sorry, 1890s to 2000, sorry, 1892, 1905. 1906 is passed away. So that's 16 years of the life, like 1890 to 1906. So very interesting years. So that's the time these innovations took place. After that, it went on sleep mode until the new person comes up. Here, what's happening is in the rapidly evolving world of AI, machine learning and system theory uncertainties are often seen as challenge to overcome. But what if uncertainty is not something to fear, but powerful force that drives the growth and evolutions? This article explores the concept of learning systems where uncertainty is embraced rather than avoided, unlocking new possibilities for innovations and adaptations. By redefining how we approach uncertainty, we bridge the gap between learning systems and unlearning systems. Quote and unquote, learning system and unlearning system. There are some system is learn better. There are some system cannot learn better. So that's exactly true in a human being also. Revolving a deeper understanding how systems evolve, adapt, and thrive in a complex dynamic environments. So this is a kind of a thematic abstract in which we, I discuss about today. There are three interesting pictures I created for you to understand. Like T is low leftmost. If you see the temperature, it is a okay. It's not a computer science. This is matter for thermodynamics or gases law by Maxwell's 1890s, right? So that point at times the temperature is a major variable which played on the gases motions. So when the temperature is very low left side, the temperature is very high in the middle. I know temperature is reasonably high in the right. If we see in the temperature is very low, the circles are close by, very reasonably close by. It's not too much distances. There you can see many circles are very close by. But when you come to the T is very high middle, there are circles too far away in many places actually. So that interdistance it is does not mean that all the circles are far away. For example, this see these two zero. There are this is a probabilistic sense only. This is not deterministic Newton's law. This is a fundamental things you all have to digest. Here we are not talking about a deterministic system. It's called a stochastic system. So there is no Newton's equation we can write for every ball here and solve that one. That is it's not a part of Maxwell's proposition actually. That's the reason he was being like out people people did not agree on it. So he went through a very, very rough and tough life actually. But what happens is, how do we don't accept certain, a formal way of writing equations, and how we are going to, manage this kind of situations where, atomic level particles, the gaseous particles, they're all moving around with the different, velocity, different, positions, and different volume and pressures, all comes into the part of, consequences actually. So there, we have Maxwell drawn this one from more of a thermodynamical concept and atomic physics level, but this is become a revolutionary in the sense that uh, how human beings brain works, how the brain is like really going to play around the games, like the combat and Boltzmann's distribution was taken as a model to model our brains. So that's the place neural networks come as a digital version of this. That's the way Professor Hinton, Geoffrey Hinton, had revolutionized. He borrowed this idea and revolutionized the learning systems. And that was in 1986. Very long back. 1986 means my undergraduate days, actually. It's amazing days. Of course, I did not know him, but 1990 we read good amount of thing on neural networks in IIT Bombay. I was a graduate student. We had a good opportunity to do that, but we did not know this kind of evolution going to happen. We just done it kind of rigorously for our own need, but we couldn't see much depth toward the way which today Professor Hinton students seen actually. Of course, we are not that level maybe, or maybe our process not taught us to that level. So, but we never realized what Toronto University students realized in 2006. What's happening here is the deep learning practitioners. There is a you can see a lot of people, kind of companies and people everyone talk about understanding how learning system evolve, adapt can directly influence the design of smarter, more efficient algorithms. A concept like adaptability, entropy, and so on and so forth is now what's happening is, uh, you know, how do you make the system to learn? And why that's how that who is going to do that, that kind of practitioner's role also coming up. It's kind of new jobs now, so it's going to come someone who can teach network better than some other people. So let's say they'll have a more skillful, they're more not they have a tricks how to teach them. It's not just algorithms actually, system theory experts. And in the comparison between learning and unlearning system adds a fresh layer of system theory. And the concept comes something learning, something unlearning, that means something missing, right? So how does the system theory people going to look at it, particularly understanding how system evolve over time and handle information? Yeah, this is a beauty. That's a place data transition going to come. Handle informations, change and the complexity. This knowledge can apply to improve complex systems designs, leading to more resilient adaptive frameworks. Okay, so I'll take you here. This is a little more focused one. I'm saying picture only focusing little more. Of course, these simulations are done in Python. Python, but you guys can do much better than me. I'm trying to construct examples. So this what's happening here is you can see red circle, green circle, yellow circle. There are can be different objects, but they were all like behaving very differently. That's what we feel that. But however, it's not that leftmost particle going the rightmost or not rightmost particle going left side. There are a kind of their own zonals, edge to edge discussion, certain things there. But as a human being, we cannot see any of this pattern on this. It's all looks like a random. Like all of the techno jam people, including all the youngsters, even professors, including me, what we can make out, nothing we can make out in this one. We'll say, oh, yeah, there are so many color circles are there. They were all like, jumping and coming down. That's the kind of inference which we can do. But we don't know anything more in and about because the kind of mathematics available not allow us to do in this. Or rather whatever we learn from classes, our professors that it doesn't allow us to write equations or something and tell about this what's happening on this around, what's the mathematical models, kind of differential equation or integral equation or algebraic equations or matrices or linear and there are so many things which we learn, right? But all those become useless for us to when this picture is this diagrams, not diagram, this simulation comes in picture. How do we going to comprehend? How do you find the pattern on it? How do we say this, even predict when what's going to happen around this? This is a central theme of all discussions on the research which have been going through rocking the AI world. So the data are there, but as a human being, we may not be able to understand because we have a limited brain, limited understanding on the complex, minute, and system detailed system. If we deploy networks, networks can understand deep learning network. That's why data transitioning to network actuals, our interesting topic. So we'll see how networks going to learn from this. Of course, introduction which I have been, telling you from the beginning, the concept of learning system deeply rooted in principle of hidden complexity. The hidden complexity. If it's known one, it's easy. Everyone can find out, correct? Of course, all of us will not be able to drive aeroplane, not because of well, because we did not know, we are not been trained on that, correct? Only some of the boys and girls can drive aeroplanes, so run the aeroplane, land aeroplane, take off land, because they were have been trained certain way to do certain things for with aeroplane. They do that. But otherwise, even though we studied so much about aeroplanes and aeronautical engineering, or even better like computer science, if someone asks us to take aeroplane from Bangalore to Chennai, so sir, bye bye, like So that's a place actually. I'm sure you are all above 18. You all know how to drive car, correct? I don't know. I'm sure most of you have a car and you would have driven the car, correct? Imagine aeroplane, thing is like we suppose it has a lot of complexity and you cannot come, handle. That's why we have a fear. So something similarly, that fear is essentially become unlearning systems. So the concept of learning system deeply rooted in principle like hidden complexity, wherein a certain unobservable unit shape the system's growth and adaptive behavior. There are many things in that we cannot observe it, but neural networks can observe it. That's what it says. This view paralleled by Ludwig Ludwig Boltzmann's theory on items, that is that unseen units significantly impact systems evolution in the contrast which we can explore unlearning systems as we one lacking such a hidden structures and therefore capacity of the complex adaptation. So what Ludwig Boltzmann said that unseen units and there are things are happening, but as a human being we are not able to see unseen things what are happening in this simulation that become informations. That information, if you're able to have a machines to see those information, then that machine is a learned systems for this simulation. Correct. Compared to us, that system will be better than some people better than us in the driving aeroplane. Like that, that neural network could do better than understanding these pictures. What the Boltzmann unobservable unit and entropy? Boltzmann's concept was there are many things, there is a error, there are many things not able to do. Even then, how do we cope up with that? That's what called unobservable. If everything observable, everything known, there is nothing to new to learn, right? New to know about it. If you know what's the questions going to come exam, there is no difficulty, right? So similarly, if we know everything in detail, then there is observable and known, but there is no issues, correct? But the issues comes here, unobservable. We couldn't have observed certain things in this. Even though it's happening, it's not comprehensible by us, correct? So that's what we call the classical thermodynamics. Boltzmann viewed atoms fundamental yet unobservables. Units, the randoms, as you see the summary of randoms, these are things confusing us actually. When this kind of confusion is there, we'll give up as an unobservable. It's highly complex. That's what we say. Then end of the story goes on to that. But what happen? Learning systems, the learning system need to find out those unobservables and those hidden complexities. That's item number 3. The learning system, whether biological like we or artificial like a deep learning network, digital one, often rely on simply observable or hidden states. Only to one thing they mostly rely on unobservable things, hidden things. These hidden layers of a system shape its the ability to process, store, apply information. The analogous to the Boltzmann atom, the components are not directly visible but act as a core deliveries of the system. See, what is happening here is why in the mathematics which we talked about, I've seen some of the mathematics for data science people, just linear algebra, probability theory. That's it. The same old bottle, sorry, same old thing, new bottle. That's all they're putting there. There's nothing new. They're trying to teach us, our children's now friends, to get into the game. Thanks. But I think I know you youngsters has to be very clean, very clear about it. See, what last 10, 15 minutes we discuss about it. It's all about it's not the classical maths what we know all about it, correct? But entropy, disorders, unobservables. Look at the terms. And do we have a tricks and traits to handle all those things? That do we have a mathematics for it? Do you have a physics for it? That's the core of this one in AI. Otherwise, we will be completely misled just knowing the matrix multiplications, linear algebra. That's not that key thing what happened in the AI. That's what everyone knows. We most of us learned very good maths in the IIT, but we never able to crack these things when we were students. But Toronto University children crack because their processes are intelligent enough to dope them as saying that make a learning systems actually, right? So it's not the maths, but the linear algebra or geometry or things, but it's all about how the physics, very well and packaged into the unnecessary maths actually. It's not unnecessary. So that the term 3.1, that's the reason I took entropy learning systems. In learning systems, when you say the system learns, what it does, an entropy might be redefined as a measure of accumulated information or experience over time. We can say learned system also experience. Unlike in thermodynamics, where entropy implies disorder and so on and so forth, right? So learning system means then what happened? We can call it as experience also in English, correct? But mathematically, how do you know? We don't have things like how do you say this boy's experience in driving aeroplane until unless we see aeroplane, correct? Do you have any mathematics on it? Like so, unlearning systems, absence of hidden complexity. So this is the most critical thing, right? So this, this it's not a funny. Actually, it's looked very easy for us to understand. Professors, teachers for a 6 months one course. Suppose any popular course. Take like mm, classical mechanics. So, I don't know whether they taught you. As in that classical mechanics process started for 6 months. As a student will go through the learning, and learning means every day they give lectures. At the end of the day, they'll go homework or something, then assignments and so on. So they'll have in semester, they'll ask us questions. When the question we able to type out whatever they wanted it, then they'll say we pass or fail. Correct? That's we call a learning system thing. But that some professors will feel that this boy cannot learn. Suppose when out of we assume that we 40 boys and students are in the class, so we say one professors in our class we go and ask sir, I want to do the project with you. Then the professor will say no, I don't want you. So because the professor made up mind that the student is not capable enough to learn things as he wants. Very politely they'll say no, I not do things like next semester I will say this. They may not accept it. The moment when they draw the conclusion is they think that the student's capability is not able to learn things what they wanted it. So that's we call the students have professor has a knowledge to classify the students' ability to learn, whether the students can learn or are not able to learn. But in digitally, how do we do? As a human being, we can do, but digitally, how we can do? We have a neural network. Can we say that this neural network can learn this one or not learn? That's a question mark. Stand still as a question mark. Maybe next Nobel Prizes, right? With comparative entropy. So what happened, unlike a learning system, unlearning system lacks the capacity to build internal order through information accumulation. Entropy observable units in the driving learning. This is a beautiful point. And the unobservable things only going to drive in the learning system. The comparison between learning and unlearning that reinforces the hidden unobservable units are essential growth of the adaptability. Just as the Boltzmann atoms underpin thermodynamic entropy, the hidden states of the learning system are central to the capacity to complexity. So what Professor Hinton, these are all the 6 points, 5 points we discussed today. These are all like what have been gone through the Professor Hinton's lectures and his papers and their thing, how he tried to figure it out, the learning system itself actually. That's what I painfully put this one, on this, one place such that I can share with you all like. In conclusion, short conclusion, what we discussed on this topic itself, interplay of learning versus unlearning system reveals the fundamental truth, adaptability and growth of the hidden complexities. Boltzmann atomic theory, though the rooted in physics, gives us a framework to understand learning systems as entities in derived and observable structures. See, this word called physics. It's not maths I learned. That's what I wanted trying to tell you today. Today, the Professor Hinton and Hofeld, they got a Nobel Prize for their work in the computer science and in the physics Nobel Prize, we see here. These unseen units drive the accumulation of knowledge, and through the system evolution, differentiating is fundamentally from the unlearning system. So, last 20 minutes actually, like 38 minutes, we went through most a difficult dry subject of the system's learnability and abilities, but what which we may not be able to comprehend. There is no equations equating, there is no if then else logic for it. So I trying to drive your mind saying that there are certain things very new, very interesting. So that's a new thing which we trying to imbibe on you all now is learning systems. That means there are unlearning system also, unlearnable. So certain students may not be able to learn. So those students might fail. because they did not learn it. So it's of course a human being might be interested because they don't want to learn, or some people not able to learn. But we are looking at the not able to learn. Networks also may not able to learn. So there are data which may not be able to convert it into network. That's what it means. What the title says actually. That will say what are the data cannot be converted into networks. That's a research topic. Data into networks. That's what we are going into that. Transitioning from data into the networks. So we said the learning systems, learnable systems, unlearned things, unobservable, all those things which we talked about. These are all essentially come from the ongoing research into neural network, and their fault tolerance has progressed significantly since 1980s. From John Hoffield pioneering work on associative memory to modern developments of deep learning and focus consistently beyond on the improving robustness of the neural network. So you can see like 1980s, that is 24 and 20, like almost like uh, 24 plus 20, 44 years, you see, 44 years of things now surfacing as things, and that resulted in like a BTech in data science, BTech in AI, BTech in cybersecurity and data science. No, these are all happened. Not 20 years before, never happened, right? And none of these universities had a BTech course in for a data science or AI. These are all happening because this, the groundbreaking results and observations which is taken by these genius people comes into the hidden pressure. John Hoffeld John Orfield is, I'll come back to this one, is foundations researchers and how the brain able to store the data mathematically comprehend. It's called John Orfield network. Please do have a time to read about him, and it's very interesting. Person who got a Nobel Prize this year. Along with the Jeffrey Hinton, professor is from Toronto University. Amazing person. He is driven the whole of AI era single-handedly because Hafils are almost given up, I think, after that when he 19. But this person, Jeffrey Hinton, never given up. In 1986, Sun was relentlessly going on for like more than 40 years to see such a massive thing in his own lifetime. Of course, Elias Suitcase was a very intelligent student of Geoffrey Hinton. He comes once from like a very good maths and very good things from Russia. I think he's a Russian born, but educated in Canada and Canadian universities, and he is one of the the star, a rock star in now in the AI industry. Of course, he's a boss of OpenAI, Elias Suitcase, but he left this company and started his own company called Safe AI. That's what is going on now. Of course, in the order we have seen some of things called Brooks Iyengar, but these people not got the prize and the fame what the left side people could see because there are it's not a kind of a thing which is same, but there are worked in when the research happening. Every professors, every people, they tend to work on their own field. They may not mix together. They won't see the correlations and things like that. This group of people very saying or they worked very differently, but a similar problem. The problems also the data, how to migrate the data into networks. These people are then also then about they also graphs and data and things are coming very close to that. We'll see the details while also reflecting on my own contributions. Of course, on my PhD time, I have done something on Euler interpolation. When the data comes, so how do we really even make a model out of it? Like, data for me those days like a complex numbers, like a network, like, airplanes, data, models, and then how do you make them as a model? After that model, how do you simulate and later on goes on? Of course, this is on went on simultaneously feedback systems also, it was very tough times. Very, very tough times. Thanks to process there, which have gone through kind of things early days. But what happened to milestones? This is I won't drive again because I did not take too much of mass into you now because you are all have a time intelligent people, intelligent students. You have a very good access to network. You can always go and Google it and learn. Of course, references given. But I want to make you all to understand the milestones. What triggers what next? There are certain things triggers something else, right? When airplane stands and the comes and land, then a lot of people come out of aeroplane. So the aeroplane standing airport is triggers many people come out of that one, correct? Like that in research also certain events triggers and other many events, like that we just look. And control theory has always been foundational in system engineering, especially in IoTs and on the real-time decision-making thing. But while AI has been certainly become a dominant in applications for the sake of predictive and automation, control theory remains a critical part of a system stabilization, optimization, and so and so. But what's happening around is, in fact, the rise of AI-powered IoT edge devices, control theory experience research, theories are come, new theories are trying to find out. People are looking at in that. And then we Hoffield 1983, Sir had a network. It's a simple network. It's like a SI, is a states which has a 0 or 1. Wij is a weight, which also 0 or 1. Then energy. So they put the network, neural network, and then they define a function called energy function. It's called Hoffield energy function. This is a foundation one. By optimizing this one, in decreasing energy level, he found that weight. That is W has become Hoffield weight, the neural network weight. That's your data become weights later. So because of certain way, but how do we going to convert the data into W, that we are still have not told you, but that's exercise will going to come down, okay? But the question is, we have to convert the data into weights. Weight is your W networks, edges, and how much they communicate to other. Weight means like there are the friends who, if you ask him that you have three friends, there are one friend come and tell more than what the person says. There are some friends may not tell us also, even though they may have gone for a movie, they will not even tell which movie they went. Nothing they tell us, so they will not tell. There are some friends partly they'll tell. Like that's neurons also same case. Sometimes some neurons will give complete information. The W may be one, sometimes zero, or sometimes in between. So how does collectively going to network? That's come the mathematical formulations is required to compute those things, which is given here. When you have a time, just look at it, right? And essentially, we have to compute this Wij. Compared to the historical perspective is that network, its networks used to find out how the data is stored. That's all. Data is stored. Our brain is data stored. Similarly, this network can be stored. So what happened? This network realized in the form of neural network. Next step. This event driven to the next step is called neural networks. Born. The birth of neural network took place because Hopfield 1980s, this foundation way of maths is handling. So the question is whether physics first or maths first, or maths first or physics first question. So when the Hopfield proposed this kind of a way neurons are interacting, then they find out what is the mathematics can be used to solve this problem. Right? That's a consequences, correct? So then optimization comes into picture. Mathematical half-field network, which is then second, you know, mm, like even took place was Geoffrey Hinton, 1986. He realized, or rather, Sir was keen on asking a few questions, not one question. He asked a few questions, unlike on Geoffrey, not Geoffrey, John Field. He, had a certain, questions which yesterday we put it in our what do you call uh, what do you call it? I'll go there actually. Is it now? Mine is in landscape. Okay.
Yes, sir.
Yes, sir, it is.
Okay. So this I did not put it in the web. So yesterday I wrote for all of you the like preliminary preparation for this today's lecture. So what Professor Hinton's question was, he asked a very different question, and like others, find the model of a given binary data. So data was Hoffman, sorry. filled as a zeros and ones binary data. So Hinton is after 3 years, that was 1983, so 1986, within 3 years. So that's the way the word binary data, you see, is not talking about very kind of video data, audio data, speech data, nothing Sarah talked about. It's original questions, which we're trying to capture what was in mind. Then we can understand, and then better we can find some new things on their way. So he asked a question called find a model of a given binary data. The word binary is a catch there. Please look at into that. So what can be done with those model emerged from the binary data? Next question is, okay, I found some model which and then what one can do with that model? Second question was, third, how probability is assigned to each binary vector. So we have thousands of binary vector we have. How do we say this vector is, some probability assigned, like, what are the probabilities, like when you talked about a certain events, whether how this vector is associated with that event. Like suppose in morning we had a weather forecasting data, time series data in the binary. Of course, the word binary still I want to know that how that data associated with the event called rain today. Giving you some loose example, don't catch me there. So it's trying to energize you all into that, but that's not exactly, but it's similar, almost like the same one, right? But then comes to how is the connected with the weights and the Boltzmann machine. This is the crux. So Hinton was the first person who conceived the idea of like, Boltzmann machine thermodynamics one, correct? But no one thought that that's going to play into the kind of this kind of thing. Even John Hopfield did not do that. Actually, John Hopfield constructed his own binary network, neural network. But what that time there is no too much of variations like a stochastic and so on and so forth. But there is a kind of catch. That catch only he logged on to that and then evolved. I mean, like Hinton. Then he was used that loopholes what John Hopfield left. There he put up a new model called Boltzmann machine. Of course, there is a new here, but it's not a new in the historically. That is completely old, 100 years before of his time of that year. And they used it to model the thermodynamical status of a gas molecules, actually molecular level of modeling that with varying temperatures. But he brought that one here. The fourth question is on that. The fifth one is how to use a Boltzmann machine to detect unusual behavior of complex system. Now comes, which I was simulating, correct? Remember the first 30 minutes we had a one box, the red circle, white circle, and all jumping around, correct? So how do we use this Boltzmann machine detect unusual behavior in the complex systems? Is any way which we can use this machine, make this machine to learn some unusual behavior from the simulation which are running. Do you remember on Python code I told you that some simple simulations, red ball, white ball running around. So now this is connection is happening now. How this machine going to learn those unusual behaviors in the given data. Then you can forget about the data, then machine will be there. And the last question is, of course, is a more of a kind of a commercial questions. That is not a foundation. Find out the state is a part of the normal state. We say, oh, it's a normal state, so okay. Or if it is not okay, then tell the person who's not found out that, right? Hey, thanks for this. I don't know who designed it. Technogen team is very nice. When you, of course, see 2,000 people are seeing that one, so it is good within the one day. Of course, here I want to take you all another 3-4 minutes and another directions. What happening was we talked more of mathematical model, energies and the network. How the Boltzmann machine came in neural network. These two events which we talked about in last 48 minutes. But in parallel, there is another interesting happened was like Madam Professor Fifi Lee from Stanford University. You just listen to her lectures. It's amazing actually. What ma'am said is that it is ma'am's view was like a computer vision. She did not go through all this what we talk about, like, Boltzmann machines and this and that. Like, I think she was moved towards from a kind of computer vision, I presume. And of course, he's in a very top university called Stanford University. Of course, there she has a lab called ImageNet Lab. That's her own lab. 2006, 7 and all, I think she started having some competitions in that, how, she'll release some pictures and then ask people to algo software to see whether the picture is detectable or not, like kind of thing, objects. That ImageNet competition become a birthplace of a lot of activities around, but AI was not used at all. It's called computer vision, pattern recognitions, and so on and so forth. But her work on collecting monumental work of, like, she was telling more than 50,000 people worked at a time in her thing, collecting the images and labeling the images, and then sorry, pre-processing the image and then labeling the image 27 cross 27. Like that, they created so many millions and millions of things. I have a data I can share with you to this. I read another article and I don't know, LinkedIn or something, which I'll share with you. Oh, exactly. Otherwise, it's available. If you listen to her lectures, you can see. So that data become like foundation. Actually, this is a place data comes. How the data come? Otherwise, data wasn't there at all. Like email data, everyone have their own emails, pictures we have, but no one put the effort to collect too much of data, like one place, and then give that kind of what you call opportunity for other scientists or engineers to do something with the data. But what is something to do with the data? See, come up with the competitions, like a yearly competition, I think, and people, students, researchers, mostly students actually, correct? And they will go and then, run this one who's identify more number of pictures, they're the first, second, third, like that's the way they'll kind of, whatever the prices and then win. But, I'll draw that one, but remember about it. The second is Ilya Sukis, where I'm from the University of Toronto. The third person is like, what is it? Professor Hinton. Professor Hinton and then Alex Kriskos. These two people, these three people jointly created a one called ImageNet, AlexNet. This AlexNet is a kind of a rock the whole thing, and they went into competition. ImageNet competition 2012. That's what I told you, 2012 unit. In the 2012, these three people, of course, Professor Hinton did not go, he's a professor, and the student Alex and Ilya Sukiswar, these two were trained that their network based on the Boltzmann machine model of Professor Hinton's idea. And that Boltzmann machines model, they introduced something called a convolutional neural network that used that network, that they understood they made that network to understand the data, when then that machines able to recognize much better than other softwares those days. It's a 2012 AlexNet paper. When you have a time, please do read. It's a very interesting paper. I'm sure you all love that one. If you have any doubts, I'll be very happy to clear and then question. It is like a foundation paper for AI, like a 2012 one, AlexNet paper. So then, a lot of activities going on. That's a, the sleeping world of image processing and, pattern recognition. All of a sudden open up, given up. Many people in the computer visions demoralized because that never given a good result. Like item 2, 3, 4 given amazing thing. And then 5, another things come up 2017. That is a third event triggers the industry now. It's a until then there is no money making industry. Like on the 2012 paper did not drive the industry to the like really like exponential way, which is that the seventh fifth one. So like the paper for attention all you need. This is Asis Aswani, Nom, and Nikki, and Jacob, Leon, Aidan, and Lucas, and Ilya Pluskov. Okay. These are the 7 author paper, I think. The 7 author paper again, given us a very good opportunity to, understand the data much better than other people's network. Okay, so their network is much better, extremely better, not much better, extremely better, superior. That's become a foundation engine called Transformers. They named it. That's become created a new companies like OpenAI and many things on that one. Of course, that's item number 6, which you see, the Boltzmann machine distribution has become alive and functional. It's become like billions and billions of things happening, events are happening by using these networks across industry, across a vertical. The seventh is CUDA, the course, the NVIDIA making that one, and then making a lot more kind of activities, and they're doing this kind of industrial things. This is what which is I talked which I talked about, like the data essentially comes from sensor or human beings, correct? Human being also you can consider sensor. That has a two part. One is deterministic, another is stochastic, and then stochastic, you have Boltzmann machine. That machine understand the data. In the deterministic case, people also went, some went to Hopfield networks. That machine also understand the data, but not the level which the Boltzmann machine understands. It understand the data very well, Of course, there is a down, you can see left side, MLP, multi-layer perceptrons and networks. They're all like trying to do some amount of understanding on a deterministic network data, but that's not as, a Nobel Prize winning level. But there is one interesting thing which I have found out when writing the book, and I saw the Prakash Iyengar algorithm exactly similarly doing in the deterministic data instead of right side of this one. That's what I see here in my book. You will see here Prakash Iyengar algorithms and very close to MLP, which I wrote 4 5 years back actually. And each sensor. Then that time we had a lot of discussion with the profs. We was not agreeing and things like that. Of course, now he's become a fan of that one after a Nobel Prize things comes for right side people. Right side means Boltzmann machine teams got the Nobel Prizes, including left side people also. It's not that only right side got the Nobel Prize. See, two ticks are there. You see, there are two ticks. On the left side, deterministic network also got John Hoffield got a Nobel Prize, shared the Nobel Prize with Hoffman, Boltzmann machine by Geoffrey Hinton's one actually. But this is what I was telling my profs. Things said this is very interesting. This diagram not drawn those kind of times to illustrate them, and then I written the period down. Also, we see you can see this paper is there in the reference. You can read when you have time. I trying to bring out all the things in one place such that the relations is calm. So our understanding is better, then we can solve the problem much better. That was my idea. There is nothing more than that. So with this, we will go to our back story, which is yeah. So we were almost done the data to networks. It's clear. If you have something, I I can break a little water. So we covered mostly into network and data, both the things. And now it's come to models, which we can talk about. If you have any short questions, I can take. I can have a little break also for all of
Yeah,
you.
definitely, sir.
Yeah.
Yeah. So everyone who has a question, you can drop one or two and save some for the end Q&A till sir will have a little break, and let's get back.
Then okay, fine. Then we can go if they not have questions. We can go to the other model, and then last one is will be very easy because we did the hard work now. First two are very hard work which we done it completed. Model is little dry area. We will complete it another 10 minutes. After that, restricted Boltzmann machine is going to be one special case of the model, which is easy for to illustrate that one. So I'll click on the model. So here what is happening, exploring interaction between physics, mathematics, and machine learning. So now I'm sure most of the credits into the data science courses, math professors will come and teach you, and physics professors will come and teach you. Machine learning may not be professors because they're all collecting their PhDs to come and teach you. Maybe another 5, 6 years, professors will have a PhDs in machine learning also. Maybe when your generation goes into that, I'm sure you will have fund the PhDs and make your parents proud. Getting a PhDs in data science and machine learning, actually. Then your generation comes to things. Then you have a PhD into that. I'm sure other two things have like a physics and mathematics. People have their own thing. But what is important thing is it's not that kind of PhDs are not. Question comes, physics goes for the patterns. Physics people, physics students, of course, all of you know physics also. I'm sure after 12th you studied physics, right? I'm sure most of you scored much better marks in physics than maths or of chemistry also, okay? So it's the case with me as well. What happens is in the physics, fundamentally when you go to lab, we do experiments. At the end of the experiment, we draw a graph, and then graph is professor already know instructors or the graph how should build the graph because they conducted experiments so many years, so they know very well how the graph will come. If the graph it doesn't look exactly the way they like, they say it's failed. That's the this student failed. Go and redo the data collection or experiments, and then resubmit. That's the way our lab courses are runs, right? So, but the fun and the background theory there is the physics mind of thing is goes for the patterns. They look for certain patterns. It might be repetitive patterns. They'll be very happy if something repeats many times. They'll say, "Oh, yeah, I found." This is called repetitive pattern. There are something may not repeat also once in a while happens. Like apple fall on the ground. That's over, correct? Apple finished cannot fall again. Same apple, correct? Maybe some other apple only has to fall. But what happens is that's kind of a non-repeated item also very important sometimes. Like, when, for example, human beings, once they die, they cannot come out, right? But these are all non-repeated items. But there are repeated items like, train coming from Chennai to Bangalore, keep morning going. So it's all repeated pattern. There is a repeated one, the non-repeated. But however, the curse for patterns, that's what, physics mind way of thinking that. But what happens is in the industrial revolutions after 1950s, essentially the world after Second World War, a lot of communication industries grown up very well across the globe. They brought out the called roll-up signal processing. Actually, the signal has to go over the line, now only wireless. Were those days over the wire, and when the wire goes, a lot of problems happening, and at the end noise corruptions and so on. So this area of signal processing come up very well. And there is a processor called Wiener process. The Wiener process is it's always look for the innovation in that one. If anything known, they subtract it. Known things is not interesting, okay, remove that. Or look at the unknown things, what is coming, that is termed as a innovation actually. So, since this there you can read it. So, the minor process called innovation. The role of signal processing always trying to find out what is a new thing is there in the data. Filter. Why do we filter known things, filter it and remove, and then bring out other data, filter data, and residual, see what other things are hiding there to find out, right? The power of artificial. So, what happened is these two are kind of found. Large philosophical thing, but what is happening, real thing is kind of power of artificial network. The artificial neural network is a kind of digital network. It's not a brain. It's not a real neuron. It's not biological neuron. It is a kind of a graph theory. We also world of computer science students, there is a graph theory. Some system engineers say it is like a network, linear network, non-linear network, and they give the name. But of course, it has its own name called artificial neural network, right? But here we connected last 1 hour of our discussion, Boltzmann machine and application, how this data become a Boltzmann machine, how it understand intricate patterns inside the data, volatile moving data, correct? And that can bring out something called anomalies and other things will come up. But this brings up the questions. Okay, the questions are interesting one. And the Professor Fifi Lee from Stanford, called ImageNet, she created a huge monster kind of a data set called ImageNet. that fed as an input to a lot of research in the AI actually. Elias Quist from Toronto and Jeffrey Hinton from Toronto and Alex Koskowski from Toronto. These three again plotted the innovation on the Boltzmann machine related networks, which can understand the data, which can convert the data into network. These three people. Of course, on the Vaswani paper, I already told, and then NVIDIA thesis. So now, if you look at the kind of Venn diagrams, math basis, and machine learning, yes, there is a kind of thing which I said in 4 5 years back. In the intersection of these diverse fields, demonstrates not only the power of interdisciplinary collaborations, but also evolving a role of AI in addressing some of the most pressing challenges of our time. This is what I wrote. But what I was, why I trying to write this was, always kind of things, the students will go through if we register for one, we are not allowed to learn other things, that stops a lot of problems when you do really complex advanced research. So when you do here in machine learning and AI thing, we need to look at this physics part of it today. I'm sure I know I shared very critical information. All of you, I'm sure you are all understood what the role of Boltzmann machines and associated network played in converting data into networks. That's a physics part of it. There is no mass, I told you, as such, apart from defining that energy function, correct? But mathematics is essentially going to play a major role. How we, data is one side, network another side. How to push the data into the network. That's called optimization problem. Bit by bit, file by image, will push into network. It's the network understand, then put another image, then until we have all images pushed into that, then we stop it. Correct. That's where math's going to come, iterative process, and that's called backpropagation algorithms. All of you, please do study. Don't miss that part, whether professor taught you or not. Study something called backpropagation algorithm. That's the only way as of now we are training these networks. So that is, you can call it as optimization algorithm, or it can be machine learning training algorithm. You can name it whatever, but essentially what happened, push data, partial data, not full data. Imagine. Olden days optimization, when we were an optimization student, we'll push all the data at a time trying to solve the function. That is impossible. That's the way it is. It's broke actually. But now what the new things here is these people taught Elias Casper and this Leah and Jeffrey Hinton and allies, partial data they're pushing to the machines. Like, not all the data, image by image. Suppose say Technojam has 70 students in that. So we are not sending 70 students image directly to network one by one. So, Anurag will image 10 of them first. Another is another student, another one. Like that, partial data, four of them, five of them. That's the learning, how the learning is happening, how the data become a network. That's we call backpropagation algorithms. Please do read it, but I did not brought out here. It is there in a place you can check it when you have time and the things. And I didn't want to bore you onto that actually. So, but it's a good one. You should learn that actually. So we that is this is now we come to the almost like a final stretch of the whole storyline which we talked about. I was keep telling that I never told you any mathematics on it. Of course, it is there. You can always go and learn it, but I want to give you the hint where you have to spend time, where you shouldn't spend time also. To say straight no to simple linear algebra, and of course you should learn, but I'm not telling no to that. But that's not the math which is used for AI. If you want to learn a math for that purpose, yes, okay. But for solving the AI problems, what kind of math is one which we are doing? It's more of physics oriented math. It's very close to physics because neural network is almost like a behaving like a biological network. Even physics failed to capture the biological network. That's another area of research is coming up. So then this is I want to draw your all of attention. See, someone is giving you like exams in paper. And they have a question. Write a program to count the number of flowers in this. I'm sure all of you jump into that. You usually write a programs wherever yellow color more is there. Then You can have, you don't need to cut AI or great things. It's just in the yellow color alone enough. So you group two places yellow colors are there, then say two flowers are there, correct? You can write so many algorithm, thousands, millions way to find this how many flowers on this picture, correct? So easy thing because that reason is two independent flowers. They are all separated long distance. So then we can, as a human being, we understand these patterns. The pattern is something the yellows all could flower form a one flower. There is a more area for a one flower. There is small area for another flower. But there are, however, there is a logic we can convert it to flower. That's human understandable things actually, right? So, but I'll take you to the another situations. Okay, these are all distributions. Please do learn when you study it. And since started that time, I'm going to quickly. Imagine this is essentially like this guy. So like Boltzmann Einstein's, sorry, not Boltzmann, Bose Einstein's statistics. Still, it's not coming to the network. You see, imagine you have a tremendous opportunity. What we talked about was only this one, Boltzmann one. This is opportunity when we talk about distinguishable, independent. There are like isolated. That's what kind of in the data. If the data looks like this, then we can do Boltzmann machine can learn from this data. Okay, but if how many of you seen this one? When you go to flower market, you see this one, right? So how do you count this? Imagine, even the professor says that you'll go 100 marks for one question paper. I don't think any one of us can attempt this question. Say, sir, please, take back this question, give some other question, for this. And the professor says that, no, no, you solve this question paper, you don't need to, write any exams. And if you solve this one, you take 100 marks and then go out happily. All of us surrender here. I don't think we have any mathematics, any physics to count here, correct? Do we have? No, correct? So, do you have a network to understand the data on this? How many, flowers on this? No. So a lot of research coming, a lot of efforts coming. It's called overlap data, intangible data. Like, I don't want to use these terms, but however, I have to tell this point at time called quantum computing. This is the situation actually. Entangled, overlapping. We don't know whether one is below or above, where we don't know clarity. Like this kind of situations actually. This is a situation where we can make a network mission, Boltzmann mission to understand this, on this kind of data. But if you have this kind of data, Boltzmann mission also breaks. So that's what I think with my experience. Then we need to have something like Bose-Einstein's statistics like Boson, they will like overlap. I know they like last year Nobel Prize went into this one only for entanglement of photons. Like you can see that over time. But this is a way which is still have a lot more opportunity for youngsters like you all to do PhDs and find out the new network models or I don't know whether network or something based on the Fermi-Dirac, this Fermi-Dirac and Bose-Einstein's models, most of them are closely come into this picture. So not easy to locate and each flowers, then we'll say some kind of course, in Tamil, we have an interesting call. I very often, sometimes, when a student is also started looking at that word in Tamil, Kuttu Madipu. Kuttu Madipu means it is not exact, I know very clearly. It is, and also it is not bad also. See what happened when you go to market, buy something. When I seen when as a youngsters when we are come from in a very interesting place called Tanjavur, we do grow a lot of paddy and associated flowers. Well, when you go to market, we don't count one by one, one by one. Give it to buyer as such. It's like we'll put a full bag of flowers or one basket of flowers. We'll have a different way of counting things like. But what really mattered me is was the kind of algebra they developed to handle such a situations actually, right? You know how if you go to KFC now or McDonald's to buy a French fries, they're not counting how many fries, one, one, one. Do they count, right? They'll They fry, they take some amount, put it in a bag, they're giving you. They think that they solve reasonably accurately, to the money which they taken from you, they given you something called French fries, large or medium. So that's a algebra and calculus, everything there in McDonald's French fries is, there is no clear cut counting like this, correct? They don't say the French fries. So many of them, 123 French fries are there into the pack which they supply to us. So there is a question mark is there, correct? There is a lot of uncertainty in it. There are, and also we feel sometime, we are taken right, we will feel uncomfortable. Then we say, measure it, weigh it, like, weighing kind of things come. So there is uncertainty, we don't want to handle it. We want to make it a more deterministic one. That time instead of counting, we go for weighing things, another parameter. But that doesn't, weighing does not going to tell us how many of them are there, correct? So there are situations like this coming up. That's what happens is, this is the most interesting question asked by Richard Feynman. uh, I'm sure you would have read in your, JE, or sorry, physics courses like payments lectures, all payments theory on them. And fundamentally, he was trying to find out, that left side is a discrete summation, correct? One, two, three, four, like right side the integrations. Are they going to equal? That's a question comes up like, can is it going to be equal? When it will be equals? That's this is kind of when you tell a French fries, from telling McDonald's, and when right side equal left side, or they can left side imagine money like 1 rupee, 2 rupee we can count. Right side we don't count. It's only so one, one, or they'll take a one bag like what do you call cover, in that they put it in queue. Then we'll say the both are equal, so we are both, French fry selling company also happy, we are also as a buyer is happy, because we agree on this equation actually. Okay, but that's not going to be the case when the machines learn. So that's a place we have an opportunity here. I think. This is my popular lecture. I learned many times to listen to this, but I'll come back to onto this. And this is what essentially happens. Like if you have, are you saying something like indigo? It's not aeroplanes. Indigo, like kind of a light, right side red, like a five patterns are there, correct? Imagine, on the binary vector distributions, looks like five of them, but incoming one is coming here on the left side, and then we wanted to find out which class of them. Like, this is a current classification problems, what hint and things like. So, but this is are all solved. What kind of mathematics if you see? Essentially, there is something called supervised learning. There is something called unsupervised learning. So we are all supervised learning, correct? Teachers taught us. So we holding degrees and we kind of formal labeling, BTech, MTech, PhD, these are all labels for us, great? Because I know teachers and professors start as formal things. But there is a lot of informal ones, like, there is unsupervised. They learn what they want, they do something, but in society doesn't recognize. But neural network also going to be same. Some networks might be learn certain things which we don't know. But there are networks which today we play something called supervised learning. There is algorithms. Apart from jokes, the reality here is supervised learning is has its own, kind of a method and apparatus. Unsupervised learning its own, its a method and apparatus called self-organizing maps, as autoencoders. These are all emerging things coming into that one. It has a different kind of mathematics and kind of way move forward into that. So here, certain things which I put it here. Mm, This is exactly kind of a thing which I talked about. It is like, anyway, I'll take this one. Another 2 minutes I'll spend on this. See, this is I'll have to draw your attention, so I'll have you with little more carefully. There you can see four greens and three yellows, correct? So what happened? The four greens are like observable. Like imagine for techno jam for me is observable to only Anurag, right? I'm only giving input and he giving output, or he give me input like V1. Anurag is a V1, and then outside output me is sitting there. But techno jam is within that right kind of boundaries. There is 100 young students are there. I do not know all of you, right? Or rather, you are not accessible to me to interact or observe. But even then, you are all forming a network called technojams. But there is a one input given to Anurag that's percolated to all of you, correct? Based on your reflections, then that Anurag sends output. From there, I'll understand what. This is what human way of network happening. Exactly ditto is a neural network also. There is input layers, there is output layer, there is a hidden layer. The hidden layer, if there is no hidden layer, the learning will be very less. And then more the hidden layer, better the learning. That's what it's not proved as such, but it appears to be true. But some of you can get prizes by disproving that. But if you say proof, or you can the formula. Also, more the hidden yellows, better the system learning. That's what the hypothesis says that. So then what happens is, if you see there, and the second one is like independently so much energy put, and then that energy only come to a network. Imagine whatever information I told Anurag, that only he going to circulate it all of you. He is not going to amplifying or not going to do this one. This way network going to be. So energy going to be constant. There is nothing new going to add it up, right? Maybe he might be adding some jokes on it, but however, information is same, which is not. But same thing for a neural network. Also, data going to be the same, but that energy level of all the data add up to that coming to that. That's the way plus energy models are doing extremely well now. This was not the case initially. Pattern recognition people never acknowledge this fact, never found out this factor called energy level models, actually, which is foundation into the field network. It's a foundation. It's continued in Professor Hinton's Maxwell Boltzmann machines. It's a this is what actually, but this was not there in a Brooks Engel algorithm. That's what I was trying to tell them actually. The moment they put energy, then there is the whole game is going up because there's something we know measured one. It is found like then we can play game out of that better games actually. This is like output. The energy what we put only is going to come out. It's not a new thing. Sometimes unobservable things may not play the game, so they may not send the new thing, but the energy come out might be less than what we sent or not the same actually. So this is the repetitive process, correct? We keep sending the input to the yellow, yellow, yellow is reflecting back until unless finally we become amicable, we know something, then we stop saying that, oh, TechnoJam learned about this one. That's what we say. Same thing neural network also. So that's what it's about. Like, here the green tool. But there are some equations and formulas which are there formulated. You can always go through that. You are all there. But I'll play my favorite things now, sure, few minutes, and then I'm sure it's that it can happen. Like this is a lecture by Professor Hinton's, so very early stage lectures. How causal model generates the data. This other case, the data generates a network, right? Sir was trying to say is that even a network can generate the data. So the reverse case of it. But however, to do that, he'll first solve that how the data become a network. Actually. Is it audible? Professor Hinton's voice is audible for all of you?
No, sir, we were not able to hear that. Maybe, sir, you can send the link.
Link is there. The link is there in that only. You can click it actually.
Sure,
So, are you the video is available? That YouTube video is coming up on that.
sir. Yeah, sir, definitely. I'll link the video in a
Our
different
time.
time as
Okay,
well.
when you since you also not have much time, so please do listen when you have a good time. So it's a great one, very good lecture. This is actually Jeffrey Hinton, Nitish Srivastava, and Kevin Swarsky, and Tashman Telman, Abel Rahman Mahmood. These are the people who really early days work. In lecture 11G, see, it's lecture 11G. My favorite one. Of course, the other thing also listen good one. 11 is a kind of a very interesting lecture which is I think it will do a lot good for you youngsters to listen to him and it'll modify your thing. So I think we are done this whole thing. The restricted we talked about kind of inputs doesn't interact with that its own. That's what we talked about it. This could go with that. So Elias Ukeswar model. The restricted Boltzmann machine is like what we talked about. It is like inputs and input here. Or maybe just go into that point I did not emphasize. Here, what happened? This is not a restricted Boltzmann machine because every units are connected everywhere. Like the green themselves connected, yellows are connected, green connected yellow. So this is a complete Boltzmann machines. But this is a very difficult problem to solve now. Input node connecting to input node itself a problem now. So that's way. But this is called restricted Boltzmann. We see V1 never connected to V2. The input nodes doesn't connect each other. They don't have edges. Similarly, hidden nodes also themselves they don't have edges, right? But they have an edge between input node to the hidden node. Similarly, next layer has second layer suppose say one pink layer, and then these things will have a restriction, wedges with that pink one. The green will not directly touch the pink. So that's called restricted Boltzmann machine. With that assumption only whole industry revolutionary thing now going on. Even today that other one is still unsolved problem only that full Boltzmann machines with this case. This case is still unsolved. It is, it is essentially that's what become unsupervised learning things which people trying to make this system to train. There is no known, well-known method and apparatus are available to train this network by the given data actually. So that's interesting. Probably look at it. I think we are almost done with the most weight, dry subject or I'll counter data, which is reasonably, but of course easy, but collecting data is not easy. It's a money, time, and it's going to make a major thing. But here we see the data essentially. Of course, this is in my book. If some of you seen my book, I've written onto that. I don't know if our university has this book or not, but maybe we should present one book next time when I come there. So, and this is the one of the page which is drawn a lot of mileage in my own understanding that gives a lot of fun. Like the world, if you look at it, data essentially they mean text data. 95% of them text data that was initially like Yahoo times when, in 2010 before. But what revolutionary things happened were when the data become image also. When the AI data science came, become the machine learning only text alone. Like, we have a regressions, auto regression, this kind of, a kind of things for the next one. It was not very popular. Machines learning and human learning more or less same, not much different. But the image data came, machines started learning more than human beings. We couldn't compete with the machines actually. And the video data comes, definitely we are out of the race because machine can see. We as a human being we can say 30 frames per second, but some of you might see 60 frames per second. If you ask me to see 120 frames per second, maybe the boys and girls who play games. I'm sure some of you might play games, correct? The people who play games, they might see more frames, like 100 frames per second. Otherwise, average people like us who doesn't play games, mostly we see 30 frames per second, but machine can see 1,000 frames per second also. So what we need have a kind of data for that. We don't have cameras which generate 1,000 frames per second, correct? If such a thing's happening, that we can have more realistic one. So now what happens in the war when the radar is there, when aeroplane is coming, enemy's aeroplane, a radar has to capture, but the enemy's aeroplane goes in a supersonic one, our radar takes over 3 milliseconds, the aeroplane would have gone different place, correct? Imagine 30 milliseconds, it's a radar has to wait one frame of data. 30 milliseconds, that aeroplane would have gone further someplace altogether. Like, there is no use of even tracking that kind of a thing. That's the kind of bad things essentially now situation happening in the surveillances. So the war is essentially very tough thing. So we need like 1,000 frames or 20,000 frames per second data. When that data comes, then we need a massive network of computers to understand that one quickly also. We don't have such kind of computers even today. Maybe some of you can start a semiconductor company. And, in fact, Anurag yesterday put it called Renano Semiconductor for me. Of course, I'm a Renano Semiconductor founder as well. I had a dream of big semiconductors in India. Not now. Now political parties are talking about it. It's at very early stage. With a great difficulty, we got a little funding and did. But unfortunately, I couldn't get a second round of funding more to continue that when added to that pandemic came, we had to shut down this company for more than 13 months without any activity. 13 months is extremely challenging for poor people like us, give money to things. So we couldn't sustain at all. So there are a lot of program make in India and things. As a poor smaller company on the smaller setup, we couldn't get anything. So I had to close down whole thing. So that's what the consequence. So I asked Anurag to remove that one. Anyway, that's so one of my baby. But even then, it is it is not in good taste because of money. Because so what happening now, the semiconductor also requires such kind of massive data processing. Now cameras are giving 30 frames per second in the video. Imagine camera giving like 1,000 frames per second. Then you record what kind of computers required to process the data or for understand the data. It's a question mark actually. Today, as we live by 2024, may not be question for 2030 or 2040 when you people live, when you become a props and talk more props, you might have seen camera for 1,000 frames per second. You would have a computers to process the massive data to convert it in a network and so. But voice is reasonably still a problem because so voice is less data, but even then the flavors are very different. Our human throat is not constant, so we have evolved our based on the mood, based on the situations, our throat will change, our formal or informal or yelling. As a human, we have a infinite variation, so the voice is not so easy to understand. So the data so less, but the variation is unbounded variation. But it's the same boy or same girl. When they talk in the good mood, they'll talk. If they're in the bad mood, they'll talk very differently. So machine cannot understand all those things now. Things are happening now that it's more a sentiment analysis more than data. And audio, of course, still more complex it is. And I told a little about radar and healthcare. These are all red eye put it because these are emerging, it's unproven things. A lot more complex things are happening. Data. But there is not much data sets on the right after that, red color, not much of data set is published and things like that. So that's the places some of a group like techno jams, they kind of people trying to get those kind of data sets and contribute it to the world, saying that and this is a data set we contributed, right? So that way your brand will be there, many people will be using your things, will be very popular, like get the credit for that actually. So you can look at that. If you see historically, if you see this is what happening, like of course, don't worry about the mass, which is will come for you later. I'll get the first one. Essentially, if you see here, text, image, and speech, audio, but we almost touched all the fourth in 2017. But the scale was not a question. The scale is number of images per second.
Sir,
Those things only become engineering, actually. We are
yeah,
almost done. And that, yeah, Anurag, you're trying to tell something?
yeah. Sir, we have a bunch of questions in chat as well. So I guess, sir, we should move for a Q&A.
Yeah, almost there. Another two minutes. I'll done with a measurement error.
Sure,
I've
sir.
almost that. That's done.
Sure.
Actually, this is the one which is given a letters of 2022 PC. Actually, it is this this also there here only. Essentially, what I want to take you one example here is sampling, which is data means a sampling. How often you have to take like a and how do you really form mathematics around that. There is a probability theory, there is information theory, there is Kolmogorov complexity. This is on the Kolmogorov is combining these two, probability and information theory for us emerging one. So here there is a one more slide to talk. After that, I'll go back into this one. This is a communication industry put on the Shannon Valley. Uh, yeah, this is what like this is a foundation problem in the communication is that reproducing at one point either exactly or approximately messes selection at another point. Why the communication means one end someone said hello, it goes to other end, that other person also listening hello. If that means communication is doing correct. If they're not able to hear hello, that means not working, right? So we send the data migrates toward the network, and then the data is reproduced also there. That's what all the world problems are, done in that there is no AI in it, real engineering things which is done in. That's a Shannon theorem, which is, but it has a limitation when it come to the kind of rate in which things which talk about satellite and things. Of course, this is my daughter drawn when she was in the fourth foot standard satellite. We made a satellite once actually. It's my favorite students from Massachusetts Technology. They had OLPC, one laptop per child. This is what it designed by that one for because it was that government has an amazing dream to give to all the people for one laptop, but unfortunately, it's not happened. So here, where is the one like 1 minute last slide? Yeah, sampling. So what happened? Data means how did data? Suppose we want to take a data set of the our techno jam students on how many pictures you want 20 picture of the person or with a same sheet shirt or a different shirt or like how many things want this called sampling actually. That is sampling is not well defined in the AI data set. So it is a very interesting area of research is happening around how many samples minimum required, how many samples maximum required. These things are it's still under questions. I'll request you to, give some time and, effort into this kind of, it's not a mass, but even then it's required a understanding on channel information theory and Kolmogorov information theory and how many samples required to train the network, whether you need 1,000 picture of Anurag or 1 million picture of Anurag or two picture of Anurag to train network, that questions are still answered, but there are some minimum number, 10, 15 people talk about, there is no mass associated with that. With this, I think I can go back to listen to other questions actually. Yeah, I'll give a control to you so you can put this there. You can take that off.
Sure, sir.
I'll stop sharing that one. So
Yeah, yeah. So I hope everybody has dropped their question in the live chat of our live. So we'll be taking some questions from there.
please take it.
So, sir, the first question is from Kushwant. He asks that what is the role of ReLU activation in LXNet?
Okay, is technical questions. What happens is one edge is connected to another edge. Like you can give all the information to say A to B, say green to we have green and then yellow, right? So the green to also has some information. That information going to yellow. Whether the green gives all the information to yellow or not, that's the question come. Then how that suppose gives a 10% of the information only gives or 100% information gives, that time there is no amplification. 10% means there is a reduction. What happens is that's the place people are putting a lot more components like saturation, nonlinear saturation, linear saturation, that kind of constructions, mathematical objects in between two nodes with weights or like sorry edges. So that's why RLU one of them. They found when they're training them, the network learns much better without that. That's the kind of observation. But there is no theoretical proof that that is must for the network. Okay. Yeah.
Yeah. So, sir, we have another question from Sayam. He asks that could you recommend tools or techniques for a beginner to explore how networks handle data?
Oh, actually, tools already recommended. We saw that presently Boltzmann machines. That too restricted Boltzmann machine. So that's the only proven tool as of now. Please, all of you, learn that one how the restricted Boltzmann machine. become a neural network model. That's one. The second thing is how do you train the neural network model by using backpropagation algorithm. Then by use that time we need a data or to train the network. And then how do you get the data from where? That's what I talked about data set also. This is what that is. Very simple one, which can go. And the website which is www.jks.com. In that DL train, the whole steps are given in principle, everything. If you do not understand it, please drop a message. Anurag has a number, or you can mail me also jks.com at jk. So, I'll be very happy to answer you all and direct. But everything you put there is nice tutorials are there in that.
Yeah. Sir, we have another question from Lakshya. He asks that what tools can be used to monitor both data flow and network performance?
Okay, there are here I wanted you all to understand the most important fundamental fact that data become a network. That's a one-time effort. Like data is a huge data is there. That data we converting it a network. It essentially means training the network. After training the network, we forget the data. We don't keep the data with us because after writing the exam, we go and throw the books, right? So we don't keep a book with us. 'Cause similarly, data go off after we learned, like a network learn. But what he asked is inferencing. There are two important events. One is a training, another is inferencing. Inferencing question only he asked. Inferencing time, we send unknown data and then see whether that data belongs to any of those probability distribution which already that network learned. If that network not learn that probability distribution, then we'll say this data are unknown. Suppose say I never trained the network with Anurag's picture, but I trained with other 10 people of that. Immediately after training all over, then I took that network and then I gave that Anurag picture. Obviously, it will not classify him as Anurag, right? So inferencing, this question belongs to inferencing. Inferencing is done by using the trained network. Okay, that time the data is new, but the network is a trained network. There is nothing changing there. Yeah.
Yeah, sir, we have another question from Ansh. He is asking that can you like explain overlaps that exist between network traffic analysis tools and big data platform tools like Hadoop or Spark?
Okay, this is a very old technology which is died now. No more it's active, but even then, whatever I understood, essentially what happened, and the big data storage is one problems, and second is transmitting the data from one machine to another machine. Also, and the second problems like so these were all managed by before 2014-15. Now these things had become a much more different now, essentially kind of that's what we talk about. Why do you push the data to the server and take the only information and that called intelligent devices called we don't want a dumb devices like 2014-15 and all. Camera sends all the data to server and then trying to do that's the way big data came. So how do all those things become now? The present scenario is emerging scenario is, for example, take a car, Tesla car. Tesla car doesn't send you all the camera data to the server, right? If it's doing that, it's no way it's going to work. It has intelligent itself. So that cameras, data goes to the onboard compute neural network there. That network understands the situation of the road data, whether it is good to drive or not to drive or the to drive. So the meaning and sense, everything happening there. So in this scenario, there is Hadoop and those things doesn't play any stand actually in the present scenario of intelligent on close to data. Initially, intelligence was not closed data. Data collected once in a dump. After that, do some manufar chart, pie chart, or some counting or thing. But now the car case, take a realistic case of car, Tesla car. Tesla car has a two cameras, front, two camera, back, side one. So six cameras has four radars, two camera radar, front, back, two, six radars, and has radars, and then have other, speedometers, everything all the data is coming on to the neural network or like a learned system which is inside the car. That system tells that road conditions, learns the road condition immediately there because it's trained to learn the road conditions, correct? If we that's the way. So a Calcutta University student trained the network very well. If IIT Bombay students not trained well, then that network going to do bad. So that's the way the new things are coming. When intelligence goes close to the data, this called problems of storage and the transmitting, become irrelevant. Yeah.
Okay, sir, we have another question, like three more left. So there is a question from Divya. She asks, how does entropy evolutionize machine learning?
Oh, that's a beautiful question, actually. This is where the foundation, which is his Professor Hinton's things come. If there is no entropy, there is nothing to learn. It's a very orderly things, correct? So we know, so, someone asked 2 plus 3, how much 5? So easy question. There is nothing to learn there. Someone said 2 plus x equal to y, what is x? Then, some unknown is there, correct? X is there. So then you put x equal to 1, 2, possible see when it will come to y. That's a combinatorial problem, correct? What happened is in the machine learning, the more the entropy, actually it learn better. That was maybe it's a PhD questions. Maybe Divya can do that. The less entropy, the system might be learning will be very slow. The more the entropy, they can change the weights very far here and there with high temperature. T is equal to very high. That on the movement of gases particles very high, so the energy level is very high. So the energy level very high, there is a good possibility that they can learn quickly, come back to uh, you know a kind of things. In fact, that's question I was, even talking physics students when it is why the children who born in November, December, their learning ability is very less compared to children who born in April, May, June. It's a hot sun, right? Our brain, the babies comes in their hot sun, their brains will be have a kind of a fully randomized. Right? Then they can learn patterns much faster than the cold weather one. That of course that disproves that theory that while Russians are much more intelligent than others because they're always in the cold, correct? So there is unknown, but what is known is entropy plays a major role in a Boltzmann machines that was not accepted when Sir was alive. In fact, he did suicide, I think, or that's but after his death also not many touched that until Professor Hinton touched that and then brought the life and then brought the new industry.
Yeah. So, sir, the last two questions, they are both from Ansh. So, Ansh is asking, in what ways we can use techniques like clustering and classification to enhance traffic routing in large scale networks.
So again, the question is the moment you put a human being, then we are biasing. If we bias the decisions, then we cannot have entropy things we are reducing entropy. Our question is directly meaning. Suppose clustering means you already define, and so all the girls will go on one side, all the boys can go. Actually, you're clustered there. So this, you brought the learning ability by 50% down. Correct. So we, as a human being, we shouldn't interfere into the neural network. That's the way there's back propagation never listen to the trainer, correct? It learns itself. So the clustering and there are old thumb rules that are failed before 2012. They were there. After 2012 election paper, those things are doesn't stand water actually.
Yeah. So, the last question that we have, sir, how do frameworks like TensorFlow and PyTorch integrate with network simulation tools? And like, how do they compare to Mininet to models and analyze network behaviors?
Okay, I think if you go to my network and my place Conchi, there is a place called Conchi. So maybe if you give me 1 minute, I'll just discuss the done question. Just for 1 minute. Why this is not happening? Yeah. So share screen. Maybe Hans can help me onto that. It will have very interesting situations here. So this is a question which is asked. Uh, okay. Are you saying something called Kansi? Kanshi? in my screen?
Yes, sir. Yes, sir.
Good. This is a answer actually. This is a network one is first based on one. Actually, he can look at this. This is there in that page only, the link. So I'll go to the answer to this question. TensorFlow, how the TensorFlow and what is another one called PyTorch is going to be used, right? So what is happening here is like if you see uh, the same neural network model is, whatever is seen, that's a model, how to train the model, to how, what you are going to use to train the model. So is a TensorFlow or PyTorch is a model framework, right? So they're not like, mathematics actually. So we can model our idea into the form of their components together. That's one are the same, that's not very different. So when to model them, we need a data, correct? How do you catch the data? We have there is called if he knows a network, he might be know something QRadar 360. But of course, there is other easy. Now QRadar become Palo Alto networks. They bought over the whole thing. Now Palo Alto networks having that one thing. Then there is tools like a tap and span, those kind of things which you put it into that. But the software flow we call Wireshark and a DC term, they'll take the data and what in the network flow, where network goes. That data, which is we want to model mathematically, correct? This is what section 4, that goes into the interesting one like this now. This is actually the code is given in the GitHub. You can see the stream of the network was near real time PCAP files and record them. And then that yellow and blue is data pipeline. This data pipeline pushed into the CNN model, conventional neural network model in TensorFlow or DL train our own. I look for it some of the good and interesting students to work on DL train, which is we have a competitive and TensorFlow, which will go for a smaller devices, cameras, and things, everything. It's not a monster like a TensorFlow, huge one. DL train, we have complete source code control, huge one. So that is goes into this, for inferencing. Then of course, rest is less same as actually. So if he's interested, he can go through this one and he can work. I think code also I put it in the where I put this code is 7 minutes. Uh, it is stop only. We are in hit up only. Yeah, the code is here only actually. So you can go there. The flow capture tools are I put and deep learning model tools. It's very primitive. Like if he works on it, and then I'll support until it's only kind of a model. Very early stage, I put this tools into that. There's a Python code also there into that, like capturing the tools and the data, and and then train the network is after training the network and then inferencing also into that. So very primitive stage it is. There. However, this answers this question of like how to snip into the network, get the data and convert the data into which can be used for training this network. After the training the network, then over the some time, then use the train network to understand whether some intruder there in the network or not. That's what the companies like Palo Alto and Fortinet, all those companies which is trying to sell their boxes and firewalls and things like that. So once it can be like this one start his own company and do this one and we train the neural network and all with the data, and then he can sell this kind of a neural networks in the market also. This is a how the pcap file become a thing. This process also put in this one very well documented. If you have any questions, it's in this candle they use UDP data and ICMP and TCP scan, all the things dumps into the pickup files. This is what I think so. I have come to this.
Yeah. So, sir, that was all questions we had, and I believe a lot of questions that we had, people have been watching really keenly to what you were saying, and we have had quite an audience today. So, yeah, thank you so much, everyone, for joining, and thank you so much, sir, for uh, giving us such an insightful session. Um, it is really an honor to have you on Math ML Math Club that we conduct. It's an idea to bridge the gap between mathematics and machine learning, since it's not only just a trend but such a revolutionary technology that we are getting to see. So, sir, thank you so much. Anything would you would like to say, sir?
Of course, I have infinitely many things to say, but however, first of all, I like to, thank you all for taking our time because it's a time everyone goes for vacation, enjoy and here and there. But I've seen very interesting souls, who want to learn new things. I was very happy to, share with whatever little I know, and also, there is something whenever you found out something. I'll always there to help. That's the main reason I made jkus.com is to support the students across the globe, essentially 5, 6 years back. Otherwise, it is extremely challenging to get onto one. So made it open, and we should bring the culture of like we also put in open source, we also invite to global attention, global health support. So where the students like to all started putting something in open source, contributed little smaller application might be wrong, so no problem. Some other person correct it. That's why open source evolves like actually. So then you will be recognized on that your domain you will be like, in fact, I've been told many companies when they go for recruitment time, if someone has a hit up, they no need to, go through any formal interview processes. Because when the hit up means the proven code, because many people seen that code, many people would have used the code, something wrong, they would have commented, the person would have changed it. So the community itself there to review and, perfect it. So companies acknowledges this card effect. Some students already maintaining hit-ups by their own open source thing. That means they're already validated by communities. They will stand the water. I think this is a very good culture we should bring up. We should give. But in India, we don't have this culture of giving. Can you see any software company like a Google or Facebook which make it open and free? No, at all. I think you younger generation, follow like what American style of like, sharing the information at zero cost and then make others also to contribute. That's the way our energy will be added up actually. Otherwise, that's the reason Dale tried from our side. Actually, my son, when he was in undergraduate times and Chennai Mathematical Institute, he wrote this one completely and see, we put it under open actually. So it has become a tool that many students, including many countries, started using it and learning it, and I know things are going on around it. Real time is useful for putting the smaller machines like ARM-based machine like PyTorch, TensorFlow. It doesn't go into smaller devices. They need a huge monster memory and things to run it like. So that's why real time. I essentially want to tell you all that be a open. Open work and trying to contribute in open source tools. I think real time one of thing we started we are all commit data science deep learning students we engineers or professors going to be take a real time and then enrich that one more and more whatever I missed it I couldn't do it certain many things you enrich that and then make it open that will stand really tall for when you guys go grow and up and up. That's what I look at.
Yeah, definitely, sir. And I would request everyone who has been joining this session, as well as every TechnoJam member, to learn from your work, get inspired from sir's work, and at least contribute back to the open source work sir has been doing. And sir, and from the entire leadership of TechnoJam, I would promise that every TechnoJam member will definitely, whoever working with machine learning and deep learning, would try to learn from your work and contribute back to it, maintaining the balance of open source as well.
Yeah.
Yeah,
Thank you, my dear. Wish you all very happy weekends and enjoy your days. Okay, thank you.
sure, sir. Thank you so much. Thank you so
Yeah.
much, everyone, for tuning in to our channel for ML Math Club. See you next time. Thank you so much. Nelly, you can close the live stream.